This podcast is about conjugate acids and bases and their place in an acid-base reaction. So first, we're going to talk about strong versus weak acids and bases. The definition of a strong acid is that it loses all of its protons. So in other words, if you put an acid in water, HX, all of the HX is going to deprotonate and all the protons are going to be attached to water and you're going to be left with X minus. And the arrow that we draw in this case is just a one-way arrow to show that it is essentially in one direction. Strong acids, these are mostly the acids that we have done calculations with so far, and that is the halogen acids, hydrochloric, hydrobromic, hydroiodic acid, and then sulfuric acid, nitric acid, and perchloric acid. So these are the 6 common strong acids. Weak acids, on the other hand, if you write their equation with water, they only lose some of their protons. So HY symbolizes a weak acid. Put it into water. The products are the same, Y minus, and the proton gets transferred to water. But here the reaction is reversible. So it can go in the forward direction and it can go in the reverse direction. And typical acids, typical weak acids have, it can vary, but somewhere around 10% at any one time of the protons are deprotonated, have come off, and the other 90% or so are still attached to HY. So this is not a totally electrolyte solution because it doesn't all ionize. A lot of it stays together. It is soluble in water, but it doesn't all deprotonate. And typical weak acids are acetic acid, phosphoric acid, and HF. The other halogen acid is a weak acid. Bases, we don't talk a lot about the difference between strong and weak bases, so I'm not going to draw reactions with it, but hydroxide bases are strong bases, which means everything that dissolves, if it dissolves, all the hydroxides come off and they are strong. Keep in mind that some hydroxides are not very soluble, but whatever is soluble is strong. Weak bases are the amine bases, such as ammonia, NH3, and the other amine bases, like the bases in base pairs in DNA. They have, bases, all ammonia-based nitrogen bases. These are weak, which means not all of them are going to generate hydroxides. Some of them are going to stay neutral. So we're going to write reactions with strong and weak acids. All of these are acids with water. They all have the same pattern. So the reaction of the acid with water, if it's a strong acid, write the arrow in only one direction and it's going to get deprotonated and then be left with the anion. If it is a weak acid, write the reversible arrow like this. So you can see they're all the same pattern. Basically, the only thing that's different between them is the weak acids show that the reactions are reversible because not all of the protons get removed. So that leads to conjugate acid-base pairs, and we are going to look at this reaction in detail in the forward direction, what's happening, and in the reverse direction. So in the forward direction, you have H2S, and it gets deprotonated to make HS minus, and because it's losing a proton, it acts as an acid. Also in the forward direction, we have NH3, which becomes NH4+, and because it is gaining a proton, accepting a proton, it's going to act as a base. If we look at the reverse reactions, we're just going to flip both reactions. So in the reverse reaction, H2S makes HS2, so this would be the reverse reaction coming from H2S, HS to HS2. So in the reverse reaction, HS minus becomes H2S because it gains a proton, it acts as a base. And in the reverse reaction, NH4 plus becomes NH3, and because it loses a proton, it acts as an acid. If we write out the complete reaction, we could see that the acid H2S becomes a base, and because it's on the other side, we call it a conjugate base. Conjugate just means on the other side of the equation. And then NH3, which acts as a base, becomes its conjugate acid. Conjugate acid bases are always sort of in pairs, and they're always separated by the gain and loss of a single proton. So in these reactions, we're going to read the reaction. All of these are important biological or environmental reactions. And we're going to label the acid and the base. You cannot necessarily tell by looking at the formulas. We have to follow the proton and figure out what happens. So H2PO4 becomes HPO4 2-, so it loses a proton. That makes it an acid, and this is its conjugate base. CO3 2- gains a proton, so it acts as a base, and HCO3- is its conjugate acid. And so go through and label these equations and then turn the video back on and check your work. So you can see if it happens where you end up labeling two acids on one side of the equation, there has to be something wrong, because it's always going to be an acid that transfers a proton to a base, leaving its a conjugate base and a conjugate acid. So they're pretty much always going to be that same pattern. It's just a matter of finding, labeling which substance gained and lost the proton. So in these charts, practice for these acids. We're going to pull off one proton and write the formula for its conjugate base. Don't forget to change the charge by, the charge has to go down by 1. And for these bases, we are going to add one proton and write the formula for its conjugate acid. And stop and do the chart and then turn it back on and check your work. So again, more practice labeling equations. Go through, figure out what gained and lost the protons, and label the acids and bases on the left, the conjugate acid and bases on the right.